So we've talked about taking derivatives with the natural log, and so now we're going to go backwards and look at functions whose derivatives involve a natural log. So let's take a look at some examples. First of all, make sure you remember this rule is a really important one. The integral of 1 over x dx is the natural log of x, plus c, of course, if it's an antiderivative. And this should make sense, because what is the derivative of the natural log of x? That's just 1 over x. So remember, going backwards gets us the antiderivative. So let's do a quick example here. The integral of 2 over x dx. The 2, of course, is a constant multiple. We're multiplying this by 2, so we could move the 2 in the front and think of it as 2 times the integral of 1 over x dx, and that gives us 2 times the natural log of x plus c. You may see when you check your answers in the back of the book, occasionally because of this natural log, what the authors will do is they'll use log properties to condense. So what they've done here is they've taken this 2 and moved it back to the exponent position. That's a rule with natural logs or logarithms called the power rule. It is not necessary that you do that. If you left the 2 in the front on a test, of course, that would be just fine. I just want you to be aware of that when you check the answers. You may see that from time to time. Oh, and it says, why is the absolute value not necessary? Well, of course, because if I put the 2 back there, anything squared is positive, so it doesn't make a difference what the argument is. Let's try this one. We've got the integral of 1 over 4x minus 1. So this looks kind of like it might involve that natural log because we have 1 over something. And what this is actually going to require is a u substitution. So think about if we let u equal 4x minus 1, the derivative of that would be 4. And so we want to solve for dx. That's the replacement we need to make. So I'm going to multiply the 4 to the other side and divide by, the derivative of u is 4x minus 1. Du dx is 4. Solve that equation for dx, and we get dx is replaced by du over 4. So then what do we have? We have 1 over u, right, because 4x minus 1 was replaced with a u, times dx, but dx was replaced with du over 4, so I move the 1/4 to the front. So I have 1/4 times the integral of 1 over u du, which is the natural log again. So we have 1/4 times the natural log of u, and then remember to replace the u with what we substituted, which was 4x minus 1. Find the area of the region bounded by the graph of the function, the x-axis, and the line x equals 3. So the function is y equals x over x squared plus 1. So I'm going to draw a picture of it. You can use your calculator or Desmos to help you. And we're looking at the function is in red there, and we want it bounded by the x-axis right here and the line x equals 3, which would stop right here. So it goes through the origin, and we're looking at this purple region right in here. So we're going to set up the integral of the function from 0 to 3. And this is going to require another u substitution. If we let u equal x squared plus 1, the derivative of that will contain an x, because the derivative of that would be 2x, and we have an x on the top. So what we need to solve for is this x dx right here. I have a replacement for the denominator. That x squared plus 1 is going to turn into a u in a second, but this x dx right here is what I need to isolate. So I multiply the dx to the other side, and I need to get x dx by itself, which means I'm going to divide by 2. So du over 2 is going to replace the x dx. I'm going to go ahead and change the limits of integration because we're doing a u substitution with a definite integral. So u of 0, remember to do that. We would take the 0 and we plug it into our expression for u. So 0 squared plus 1, of course, is 1. Same thing with the 3. Plug that in for x. We get 3 squared plus 1, which gives me 10. So I have the integral from 1 to 10 of 1 over u du. But remember, let me say that again. 1 over u, and then the x dx was replaced with du over 2, so I moved the 1/2 to the front. There's where the natural log comes in, because I'm down to 1 over u du inside my integrand. So that gives me natural log of u times 1/2 on the interval from 1 to 10, because we changed the limits of integration. So we've got natural log of 10 minus natural log of 1. Natural log of 1 is 0. Put this in the calculator, we get 1.151. Let's try this one. We've got the integral of 3x squared plus 1 all over x cubed plus x dx. Again, can we let u equal the denominator? If we can let u equal to the denominator, Let's see if that gets us somewhere. So if u is x cubed plus x, what is the derivative of that? That is 3x squared plus 1, which is exactly what we need in the integrand. We need 3x squared plus 1 times dx. So du dx is 3x squared plus 1, multiply the dx to the other side, and there's our substitution. So we have 1 over u, and then the 3x squared plus 1 dx replaces with du. So we just have the natural log of x cubed plus x plus c. We should have the absolute value in there because that we technically can't take the log of a negative number. If you forget that and you just write parentheses, that's fine. Let's try this one, the integral of secant squared x over tan x. So can we let u equal the denominator, tan x? If we do that, the derivative is secant squared x, dx. So du is going to replace the secant squared x dx. So we have 1 over u du again, which is the natural log of tangent x. Let's try this one. Integral of x squared plus x plus 1 all over x squared plus 1. This one's a little bit more challenging because if we let u equal the denominator, the derivative will just be 2x, but that doesn't really account for what I have in the numerator. So I'm going to try a different technique here, and this is where we're going to start to get into some more complicated techniques, and we're going to keep working on these for the next couple of units. And one technique is to try breaking this up. Let's see if we can do something with this integrand that will allow us to work. So what I did is I broke this up. I'm going to break this up using long division. So I've got the numerator, x squared plus x plus 1 goes inside the division sign. X squared plus 1 is in the front. And we can go over where I'm getting this again in class together. So don't worry so much about where I'm getting this. Just take my word for it for now that when we do long division, remind me to go over this because I want to show you how we got it. When we do long division, it breaks down to 1 plus x over x squared plus 1. So now let's integrate that expression and see if we can get a u substitution to work for that second part. The integral of 1, that's no big deal, but the integral of x over x squared plus 1, if we separate these, we can do a u substitution with the x squared plus 1. The derivative will be 2x, and we need to solve for x dx. So I'm going to divide by 2, multiply by dx, and that integrand turns into 1/2 times 1 over u du. So we have the integral of 1 dx was just x. The integral of 1/2 times the integral of 1 over u du is 1/2 natural log of u, and then just remember to make your substitution for the u. Let's try this one. We've got the integral of 2x over x plus 1 quantity squared. So I'm going to try letting u equal x plus 1. The derivative, of course, is just 1. I still have the x in the numerator. What can we do with the x in the numerator? Well, notice that we can take this expression, this u equals x plus 1 expression, and we can solve for x. Let's see if that does something for us. If we move the 1 to the other side, we get x equals u minus 1. So this is what I have. Take a look. I took the 2 to the front because it's a constant multiple. The numerator became u minus 1. The denominator became u squared because of the original u substitution, and the dx got replaced with du. Now this I can work with because now that I have a single term in the denominator, I can separate the numerator into two terms. So I separated the numerator into u over u squared, which reduces to 1 over u, minus 1 over u squared, which stays 1 over u squared. So 1 over u du is just the natural log of u. That's not a problem. 1 over u squared is going to be a power rule. That's u to the negative second. So that becomes u to the negative first over negative 1. The 1 over u du turned into natural log of u. Clean it up a little bit and go back and make your substitutions for u. Okay, so I've got a separate PowerPoint here, but I'm just going to do a few more examples that involve integrating when there's a natural log. So some general tips to kind of keep in mind as we go through these. Know your basic integration rules. So of course, remember the power rule, the log rule, natural log rule, and the rules for the trigonometric functions. Find an integration formula that resembles all or part of the integrand, and that's what we're trying to do with these natural logs. If necessary, find a choice for u that will make the integrand conform to, say, 1 over u du, so we can use the natural log, for example. And then if that doesn't work, try altering the integrand using algebra in some way, like long division, or maybe using a trig identity. So let's try this example. It says solve the differential equation. So we have dy dx equals 1 over x times the natural log of x. So don't let the directions throw you. We're still integrating. Remember, to solve a differential equation, we want to separate the variables. That means we're going to move the dx to the other side where the x terms are. I'm going to leave the dy where it is, and we're going to integrate both sides. So the left side is the easy part. The integral of dy, there's like a 1 in front of that. That's just y. So our final answer is going to be y equals some function of x. The right side is where we got to do the work. So I'm thinking we can do a u substitution here. If we let u equal the natural log of x, think a step ahead, and that's what you want to really think about with these u substitutions. If I let u equal this, its derivative will contain this. And if that, whatever it contains is already in your integrand, then that's your choice of u. So if I let u equal natural log of x, the derivative would be 1 over x. So du would be 1 over x dx. And that's what you have in the integral. Do you see that? Because you have an x in the denominator and a dx in the top. So then we end up with 1 over u du, and that of course becomes the natural log of u, and u just a second ago, remember, was natural log of x. So we have y equals natural log of x plus c. Looks kind of strange, but that's what we have. Let's try this one, the integral of tangent x dx. We haven't learned the integral of tangent x. There is a formula out there, but let's go ahead and write this as sine x over cosine x and see if we can figure it out. So if I let u equal cosine x, what is the derivative of cosine x? Well, it's negative sine x. I have a sine x in the numerator, which is good. I'm going to move the negative to where the du is, so we end up with negative 1 over u du, which is the negative natural log of u, and remember u we said was cosine x. So the integral of tangent x is negative natural log of cosine x plus c. You can memorize this if you want to. I wouldn't bother. I think if you can just remember that tangent x is sine over cosine x, if you ever need to figure it out, you can do it this way. Let's try this one, the integral of secant x dx. So I'm going to write this as, well, actually, okay, I did something a little different here. I was thinking first, let's write it as 1 over cosine, but that's not going to get us very far. So there's a different technique here. What I did is I multiplied secant x by secant x plus tangent x on the top and bottom. I'm doing that because I'm just multiplying by 1. Now, where did I get secant x plus tangent x? Don't worry about it. I'm not going to ask you to reproduce this on a test, but I want you to see this technique of multiplying by the same thing on the top and the bottom, because all you're doing is multiplying by 1. So what does that give me? That gives me secant squared x plus secant x tangent x on the top over secant x plus tangent x on the bottom. I'm going to let u equal secant x plus tangent x, which is the denominator. And the reason I'm doing that is because I know my trig rules, and I know that the derivative of secant x is secant x tan x, and the derivative of tangent x is secant squared x. That, you'll notice, is exactly what you have in your numerator here. So then this turns into integral of 1 over u du, which is the natural log of secant x plus tangent x. So the integral for secant x is the natural log of secant x plus tangent x. So all 6 of our trig functions now have an antiderivative. We didn't do tangent x and secant x. We didn't do those in Calc 1 because we hadn't dealt with natural logs. Now we have them. So, of course, we know the integral of sine and the integral of cosine. Now we have the integral of tangent x, the integral of secant x, and I didn't work them out, but here's the integral of cotangent x and the integral of cosecant x. So add these to your list somewhere for your trig integrals. Let's try this one, the integral of 1 plus tan squared x dx, and they want me to evaluate this. It's a definite integral from 0 to pi over 4. So 1 plus tan squared x, you may or may not remember, it's okay. That's the secant squared x is what that's equivalent to from pre-calculus. That's a trig identity. So the square root of secant squared x, of course, is just secant x. We have the antiderivative for secant x. That's the natural log of secant x plus tan x. No u sub was needed here because I just knew the antiderivative of secant x from the previous slide. We're going to evaluate it from 0 to pi over 4, so I need to use the fundamental theorem of calculus. So I've got the natural log of secant of pi over 4 plus tangent of pi over 4, which is the square root of 2 plus 1. minus the natural log of secant of 0 plus tangent of 0, which is 1. So that gives me this. Solve the differential equation. This time they gave us a value, 1, 0. So if we move dx to the other side, I put the 3 in the front. I'm going to do a u substitution. We're going to let u equal 2 minus x. The derivative would be negative 1. So dx gets replaced with negative du. So then pause the video. Make sure you get it from here. We've got negative 3 times the natural log of u, which is 2 minus x. Now they gave us an initial condition 1, 0. So I'm going to plug that in. And I'm going to solve for c, and I get a value of 0 for c. So my final answer looks like this.